everybody. Today we're going to be covering topics 2.1 and 2.2. 2.1 is about velocity, position, and acceleration. So first we're going to start with some definitions. Some of those we've already talked about. First we'll define kinematics. It's the branch of physics that describes the motion of objects. So unit 1 was about why things move, which is forces. Things accelerate when there's a net force applied to them. And now we're going to describe that motion in terms of where things are, how fast they're going, and if they're accelerating or not. So we've got two different types of quantities. We have scalar quantities. These are quantities with a magnitude, but no direction. Our two quantities for now are going to be distance, which distance we'll use a lowercase d, it's measured in meters, and that's the total path traveled. But there's no direction. I'm not saying I'm traveling to the right or left, I'm just traveling. And then the other scalar quantity is going to be speed. So that has no direction, that's just the rate of change of distance. So speed is just distance over time. But again, there's no direction. I'm not turning right or left, I'm just going. Compared to vector quantities, which we've talked about, those quantities have a magnitude and a direction. And there are three for this unit. We have defined them before, so just going to quickly run through those. We have position, which is in the x direction or the y direction. It's measured in meters. Okay. And if we have a graph of position versus time, let's say it looks something like this. The slope, so rise over run, we rise meters, we run seconds. The slope is velocity. Velocity is the rate of change of position. So remember our average velocity equation is change in x over change in time. That's my average velocity. And if we have a graph of velocity versus time, let's say we're increasing our velocity, the slope of this graph will be our acceleration. And the area under the curve is going to be our displacement. And acceleration, that is our rate of change of velocity. So our average acceleration is going to be our change in velocity over change in time. Again, that's my average. We won't usually see an acceleration time graph, but if you do, let's say we're changing our acceleration, the area under the curve here is our change in velocity. And for those in calculus, the slope of this graph is called jerk. We don't need to talk about that for this class though. So let's do an example. We're going to sketch the distance versus time, position versus time, and velocity versus time for this scenario. So we walk 15 meters in 10 seconds out to the mailbox. We check the mail for 10 seconds so that we're assuming that we're not changing our position here. We're standing still. And then we run back in 5 seconds. Let's sketch the distance, position, and velocity time graphs. So let's start with the distance. Okay. We're going to walk 15 meters in 10 seconds. It's not going to be the most accurate graph, but I'm just walking 15 meters in 10 seconds. Assume that's a straight line. We're going to check the mail for 10 seconds, so we're not going to move. So let's add another 10 seconds on here to 20 seconds. We're just going to stay here. 5 seconds go by, so we're out to 25 seconds. We run back. So with distance, we're just interested in the total distance we travel. So we're going to travel another 15 meters, so we're going to have a total distance of 30 meters traveled. And so it'll take us 5 more seconds to get there, so looks something like that. Okay. that is our total distance traveled. If you're, wearing, something that measured your steps, it would say you traveled 30 meters. So the difference here in our position versus time, position is actually where we started. So here's our house over here. We started here. This is, say, x equals 0. And over here at x equals 15, this is the mailbox. Okay. So we walk out to the mailbox, but then we're going to run back to where we started. So we want to end up at that same location. So the difference here is that this last piece, this last part where I increased my distance further, I have to make it back to the x-axis. So start at 0, 10 seconds later, I'm out here at 15 meters. So that part looks the same. I stand still for 10 seconds. But then I have to get back to where I started, back to the x-axis at 25 seconds. So it looks like that. And then the last one, velocity versus time. Okay. We're going to look at the slope of our position time graph. So for this first 10 seconds, I'm traveling 15 meters over 10 seconds, or my velocity is 1.5 meters per second. And I'm assuming I'm moving at a constant rate, so it's just going to be a horizontal line. I'm traveling 1.5 meters per second for that whole 10 seconds. Then for the next 10 seconds, my slope is 0. I'm not moving. So I'm just going to have a horizontal line here. You can kind of, there we go, dash those if you want. And then my last 5 seconds, the slope is down 15 over 5, or negative 3. So down here at negative 3 meters per second for 5 seconds. That's my velocity running back towards the house. And just for fun, let's think about this graph here of my velocity versus time. Let's say I wanted to know, I had another question here that was, what's the displacement? And remember, displacement is my final minus my initial location, okay, which should be 0. I start at 0, I end at 0. 0 minus 0 is 0. But we could also figure that out from this graph here by looking at the area. Okay. So area under the curve here. So the area of this first section here is 1.5 times 10. This is positive 15 meters. But then I'm going to have a negative area here underneath the curve. And this is negative 3 times 5. So negative 15 meters. For a total area, 15 plus negative 15 is 0. So my change in position, my displacement is 0 meters. All right, let's move on to 2.2, which is kinematics in 1 dimension. We're going to start with some equations. So these are the 3 equations that we will use throughout the rest of this unit. These are our constant acceleration equations. So we're going to deal with situations where we don't have a changing acceleration, we have a constant acceleration. So our first equation is going to be velocity, that's going to be our final velocity, equals our initial velocity, that little 0 there means initial, plus acceleration times time. So that little 0 means initial, and you might hear me say V naught. Naught is the word for that little symbol there, and it just means initial. That first equation is actually just our acceleration equals change in velocity over change in time, just rearranged. Okay, so that's our first equation. Our next equation is the long one. Our final position equals our initial position, x naught, plus our initial velocity times time, plus 1/2 times our acceleration times t squared. And then our last equation is going to be our final velocity squared equals our initial velocity squared plus 2 times our acceleration times our displacement. If you want to know where these equations came from, ask me in class. So steps for using the problems, steps for solving problems using these equations. First, I'm going to recommend that you list your known and unknown quantities. And then we'll choose the equations based on what we know and what we need to find out. So there's 3 equations, but some will be useful and some won't be. Pick the one that works and we'll substitute and solve. So let's do a couple examples. We have a plane that accelerates at 2 meters per second squared and needs to make it to 27.8 meters per second to take off. How long does the runway need to be? So this 2 meters per second squared, I'm going to list that as a known. We know our acceleration needs to be 2 meters per second squared. This is our final velocity. So our final velocity needs to be 27.8 meters per second. We can assume that our initial velocity is 0 because we're starting from rest. So that's what we know. And then what we need to know is our final distance. And we can assume that we also start from 0. So our initial position is 0 meters. So then looking back at our equations, we have information about velocity and acceleration. We need position. Our first 2 equations deal with time. I don't need to know time for this problem, so I might look at this third equation, final velocity, initial velocity, and acceleration, and then we can solve for position. Cool. So v squared equals initial v squared plus 2ax. I'm just putting x here because that's delta x. Our initial is 0, so it's just going to be our final position there. So our final velocity is 27.8 squared equals 0 squared plus 2 times x. So let's just divide by 4 here to give us our position. And it looks like x needs to be 193 meters so that we can take off for our plane. All right, next one. We drop an egg from a 50-meter tall building. How fast will it be traveling when it hits the ground, and how long does it take to fall? So here's our situation. We're up here at 50 meters. And we drop an egg from the top, and it falls down. So we know that, let's write things in the y direction. So our initial y is 50 meters, and our final y is 0 meters. And we actually do know the acceleration. Acceleration is going to be g, which is negative 9.8 meters per second squared. So first question, we want to figure out how fast it's going when it hits the ground. So we want to know our final velocity. We can assume our initial velocity is 0. So let's use that same equation we just used. V squared equals initial v squared plus 2 times a times our change in position. So 2 times negative 9.8 times final minus initial position. So then to solve for v here, let's take a square root of both sides. The negatives should cancel here, so v is going to be the square root of 2 times 9.8 times 50. which gives us a velocity of 31.3 meters per second. And then how long does it take to fall? You can use either one of those other equations. Let's go with the shorter one because that seems easier. So velocity equals initial velocity plus AT. When it gets to the bottom here, it will be traveling down. We took a square root here, so this really could be plus or minus. Look at the scenario to figure out if it's plus or minus. It's going to be a negative 31.3. So negative 31.3 equals 0 plus negative 9.8 times t. So 31.3 divided by 9.8 gives us about 3.2 seconds.